Good evening and welcome to another edition of Monday Night Calculus. I'm here with Steve Kokoska and Tom Dick. My name is Curtis Brown. I'm with Texas Instruments, and we are so happy to have you guys here tonight. We're going to be talking about some really cool calculus tonight. Steve and Tom have some really neat things lined up for us. There was a pun there. Hopefully you guys caught it. And we're going to have a lot of fun. As we get started, though, I'd love to have you guys posting in the chat here or in the comment section about where you are from, where you're watching from, and then also please interact with us, ask questions, interrupt us. Steve's going to ask some questions and be prepared to do a little calculus or at least give your gut response on these things. He might make me make a couple of comments and I might embarrass myself. We'll just see what happens. And then Tom's going to do a little bit of technology expertise, and we're looking forward to that. So Steve, if you want to, you can go ahead and take it away.
All righty, here we go. I'm going to share my screen. There we go. Hope that's working. Here we go. Can you see that, Curtis?
I can see it. It looks good.
All right, fantastic. I'm going to just try to make that just a fuzz bigger if I can. And there we go. How's that? Okay. Well, thank you very much, Curtis, for arranging all of this. Carrie, thanks for your technical expertise. Tom, it's always a blast working with you. You know, I forgot to remind you about this. I haven't heard much from the DYDXFL. Maybe you talk a little bit about that when it's when you take over. We should thank Mark Corrali again. He's done a great job of advertising all of this on his Facebook page, and he's passed along some good questions. I apologize, Curtis. I do want to acknowledge all of our AP Calculus teachers and students in Canada, especially at Strathcona High School in Edmonton. And I want to remind the teachers who are watching, you know, we originally designed this for teachers, but we would love to have students participate in all of this and actually ask and answer some questions.
And actually, Steve, on that, I forgot to put one little thing in my intro, and that was that we continue to use this and post this on the TI bulletin board. I'll put a link here in the chat momentarily. And that's the location where teachers and or students can go and either access the old videos of previous Monday Night Calculus, and they can access the materials, the solutions to previous ones, and the questions and problems that you have prepared for the upcoming session. So just a heads up, I would highly encourage teachers to be using this with their students as we go along through the semester.
Very cool. Well, tonight's topic is local linearity and Hopital's rule. And what I'm going to do is actually talk a little bit about Hopital's rule. I'm going to try to motivate the idea why we need something like this and solve a couple of problems using Hopital's rule. I'm going to take a look at the problems that we posted earlier, and then I'm going to pass it over to Tom, who'll look a little bit at local linearity in more depth with technology, and I think a really cool application with technology that he developed. So let's start out by taking a look at this particular function and a limit. This one is capital F of x, which is the log of x divided by x minus 1. And what I'd like to do is to find out what's going on with this function near 1. Now, what I'd like to do, I guess, initially, and what what our gut reaction is to do is to try to plug in x equal 1. And if we plug in x equal 1 in the numerator up here, we get the log of 1, which is 0. And in the denominator, we get a 0. And we know right away here that something's up. We know that x equal 1 is not in the domain of this function. There's no way we can figure out this limit by direct substitution. So if we take a look at the limit of the numerator, as x goes to 1, well, again, the log is going to the log of 1, which is 0. And as x goes to 1 of this expression, well, that's pretty easy to figure out. That's a continuous function. It's a simple polynomial. That limit is 0 also. So this limit is in the form of 0 over 0. It's in an indeterminate form of 0 over 0, and we need a way to handle this. Now, before I come up with it, before I figure out how to handle that kind of a limit, I do want to remind you that we do have some other solution techniques. Now, they don't necessarily work on this kind of a problem, but you've probably, at this point in the class, looked at problems like this, where you take a look at the limit as x goes to a of a rational function. And sometimes we're able to factor and cancel. And in this case, I was able to cancel the x minus 1s. And the way that I like to look at this is that this function right here and this function are exactly the same everywhere except that x equal 1. So if I want to know what this function is doing near x equal 1, I can ask, well, what's this function doing near x equal 1? And this one's easy. I can find that limit by direct substitution. So, excuse me, that's a common solution technique that you've probably looked at already. You've been studying limits, I know. And this particular limit, we looked at actually, Curtis, last week, kind of a nice segue here. We looked at this one last week when we were considering the limit of some trigonometric functions. This limit occurred when we looked at the limit, the derivative of the sine function, and we went back to definition. And that limit occurred, and one way to solve that one is with sort of a not complicated, but a long geometric argument. So the point is that there are some other techniques to handle 0 over 0, but neither one of those work in this particular case. So I'll get a technique in a minute. I want to take a look at another possibility. Let's take a look at that exact same function, the log of x divided by x minus 1, and let's see what happens as x goes off to infinity. I'm going to try to scribble a little bit here, Curtis. I hope it shows up. If I take a look at the limit as x goes to infinity of the log of x, well, as x increases without bound, so does the log of x. Just think about the graph. I know that your students have studied this extensively. This goes off to infinity. And if I take a look at the limit as x goes to infinity of x minus 1, that limit, that function also increases without bound and goes off to infinity. So in this case, both the numerator and the denominator are increasing without bound. And this is an indeterminate form of type infinity over infinity. And I don't have a way to solve this one. And just thinking a little bit about this naively here, just thinking about what this limit could be, you know, if the log of x is increasing a lot faster than the denominator, then that might be driving this entire function off to infinity. On the other hand, if the denominator is increasing faster than the numerator, then it might be driving the whole function to 0. And a third possibility is that there's some sort of compromise, and it might be going to some constant. Now, we do have some other techniques here, or at least one other solution technique. Let's not forget these. You've probably studied this already. If I want the limit of a rational function, if I have the quotient of two polynomials as x goes off to infinity, one technique here is to multiply or divide the top and the bottom, the numerator and the denominator, by x raised to the largest power in the denominator. If we do that in a little simplification, I know what these two expressions are doing as x increases without bound. Both of those are going to 0, and this might look like a 1, but it's really a 0. So that expression is actually going to 2/5. So, okay, we need a way to solve these sorts of problems. I won't read through all of this with you. L'Hopital's rule gives us a way to deal with these kind of indeterminate forms, 0 over 0 or infinity over infinity. And it basically says if we have one of those indeterminate forms, then the limit of our original expression is the limit as x goes to a of the derivative of the numerator divided by the derivative of the denominator. So the f prime divided by g prime. And by the way, one thing that we don't often see in some of these examples is, you know, we might take the derivative of the top and the derivative of the bottom. And you know, when we evaluate the limit might not exist. I think sometimes we think, well, when we execute L'Hopital's rule, we've got to get a finite number. Not necessarily true. It is possible that the limit may not exist. Now, this is an important theorem, clearly. And I'm going to take what I call a closer look at this. So L'Hopital's rule says in word, the limit of a quotient of functions is the limit of the quotient of their derivatives provided that the conditions exist. So remember that you need to make sure that the conditions are indeed satisfied. What that means is that we do indeed have an indeterminate form of type 0 over 0 or infinity over infinity. In other words, you can't just arbitrarily apply L'Hopital's rule. You've got to make sure that these conditions are satisfied. Now, another common error that I see here on grading some of these AP exams is sometimes students will check to make sure that the conditions are satisfied and then incorrectly apply the quotient rule because, well, darn it, I have a quotient of functions. And that, of course, is incorrect. So the second thing here is that L'Hopital's rule is actually valid for one-sided limits and for limits at infinity or negative infinity. So if the limit is any one of those and we have an indeterminate form, L'Hopital's rule works. Now, I think that at least one special case here, we can prove. And I think this is accessible to your AP Calculus students. So I'm going to take a quick look at this. And Curtis, if it's okay, I know there's a little bit of a delay here, but I'm going to try to ask a couple of questions because I think there's a couple of nice things going on here, okay? So I'm going to try to prove this by working backwards. I'm going to assume that f of a equals g of a is 0. Again, this is a special case. F prime and G prime are continuous and G prime of A is not equal to 0. So I'm going to work backwards. I'm going to start with the limit as x goes to A of F prime over G prime of A, and I claim that that is equal to F prime of A divided by G prime of A. So my first question is, why is that true? Why can I evaluate that limit by simply plugging in A? And I know that that's the answer. And I know that there's a little bit of a lag here. And I've got some hints off to the side, but let's see if we can get some other answers here. Now, from there, what I'm going to do is I'm going to take a look at both the numerator and the denominator, and I'm going to write that derivative according to definition. Now, this is what I call personally, the alternate definition of the derivative. You know, now this isn't the one where the limit as h goes to 0, but this is the alternate definition of the derivative, what I call the alternate. Some people actually like to start with this one and feel it's more natural. That's fine. And then what I'm going to do is make one more step here. I'm going to make use of some properties of limits. I know that both of these limits exist. So the limit of a quotient is the quotient of the limits, sort of again working backwards. And then let's see if I've done everything correct here. The x minus a's cancel. And let's see. I know that f of a is 0, g of a is 0. I'm in this special case. And so that's just the limit as x goes to a of f of x divided by g of x. And that's what I wanted to prove. So this is a special case, but again, I think there's a lot of nice AP calculus concepts going on there. I think very accessible. And again, why can I make this step? Well, that's because I know that f prime and g prime are continuous. And remember, if I have a continuous function, I can evaluate the limit by simply direct substitution. And that's kind of cool. Now, Tom's going to show you a better illustration of this, but I'm going to show you a couple of graphs. This is an illustration of the same situation graphically, all right? I'm going to try to do this here. So I have these two functions, f and g. Remember I said that f of a and g of a was equal to 0. And then what I did is I sort of zoomed in near a. And remember, since these are nice, smooth, continuous functions, I know that their derivatives exist. That means as I zoom in around A, the graphs look like straight lines. So you can almost think of these as equations of the tangent line. Okay, remember that f of a and g of a are equal to 0. So plus f of a is on one end and plus g of a is on the other end of that expression, but they're both 0. So that means the ratio here of f of x divided by g of x is approximately equal to the ratio right there, the slope of the tangent lines, because near A, F is like its tangent line. Near A, G is like its tangent line. But in this particular case, the x minus a's will cancel. I'm left with the ratio of the slopes. And what is this really? That's f prime of A. That's g prime of A. And that's a really nice visualization of that. And Tom will show you a little bit better way, I think, to see that on the calculator, but that's kind of cool. All right, I'm going to try a couple of examples. Curtis, any questions at all? Anything come through? Uh-oh, I lost you, Curtis.
I'm sorry, Steve. I had muted myself and completely forgot.
Anything at all?
We have not seen any questions come in. So, and no comments either, no answers to your questions.
Oh,
so
no.
I challenge everyone to go ahead and do a little bit of calculus and respond. I responded a couple of times, but my microphone was muted.
Okay. All right. Well, let's go back to this original example that we started this evening out with. Let's take a look at the limit. As x goes to 1 of the log of x divided by x minus 1, first thing we have to do is to verify the conditions. So I think we took a look at this a little while ago. The limit as x goes to 1 of the log of x is 0. The limit as x goes to 1 of x minus 1 is 0. So indeed, this limit is in an indeterminate form of type 0 over 0, and we can apply L'Hopital's rule. I'm going to step aside just for a second. Curtis, we may have mentioned this previously, but I'm going to do it again. I'm going to write something up here. You know, they always tell you never write anything on the board or on the screen that's wrong, but I'm going to write this anyway. I just want to remind everyone that this is not acceptable as of right now on the AP Calculus exam. So we're often, or many of us are used to verifying L'Hopital's rule by writing something like that, by writing the limit as x goes to 1 of the log of x divided by x minus 1 is 0 over 0. I will tell you that in my class that is acceptable, but on the AP exam right now that is not acceptable. And what bothers people, again, as a reminder, is that equal sign. So you cannot write this. If you write that, if a student writes that and then goes on to apply L'Hopital's rule, we will read with them, but they will lose a point for an incorrect verification of L'Hopital's rule. So the natural question is, I think, how do you verify L'Hopital's rule? And it's right here in this line. The students need to take a look at both the numerator and the denominator separately. And it would be nice to add a little bit here. I'll put 3 dots. Therefore, the original limit is in an indeterminate form of type 0 over 0, and L'Hopital's rule applies. All right, so let's see. I can take the limit now.
That's a good reminder, Steve. Thanks.
I think it is. You know, when I was the chief reader, Curtis, it was okay to write that, but there's been a little bit of change. And I think we may have talked about this before. You know, I have a little bit of a problem with something like this. The limit as x goes to infinity of the log of x. Well, you know, this isn't really right either because infinity is not a number, but we all understand what that means. We as mathematicians, as AP Calculus students and teachers, understand that symbolism and that notation, and we know what that means. I'm not sure I understand the difference between that one and this one, but nevertheless, we'll follow the guidelines. So, all right, we'll apply L'Hopital's rule. We got to take the derivative of the numerator divided by the derivative of the denominator. Derivative in the denominator is easy. That's 1 in the numerator. Pretty easy also, 1 divided by x. I'll do a little bit of simplification. And now that limit is really easy. So that's just 1 divided by 1 or 1. Pretty cool. Now, one thing that I did not do, excuse me, Curtis, in these problems or in these examples is I didn't take a look at these with technology, but I would like to encourage you, your students, to do so. Now, once you solve this analytically, or even before you solve it analytically, it's kind of a neat idea to graph the original function near 1 and see what technology suggests the limit is, and see if you can back it up analytically.
I like that a lot. That makes it visual for me as a student. I can think a little bit about it. before I start to try to get into the pencil paper work of actually doing this limit. And I also want to comment that Mark Crowley just commented that he said to tell his students to just cross it out because like it never happened. He says, write it down and
what's
then
this up here? Cross it out. That's right. We don't read crossed out work. He's absolutely correct. He's absolutely correct. And, Curtis, this brings to mind something that Tom and I talked about, many years ago when calculators were first introduced. How do you use technology to its fullest capacity, fullest extent? And I really firmly believe that I should use technology to explore a possible solution to a problem, then solve it analytically, and then use technology to confirm my results. And that's exactly what you just said, that three-step process. And I believe very strongly in that. So excellent point. All right, I really like this one. This is a classic, and I'll have to ask a question or two about this one. Let's find the limit as x goes off to infinity of e to the x divided by x squared. First thing we'll do is verify the conditions. As x goes off to infinity, e to the x increases without bound. As x goes off to infinity, so does this easy polynomial. That increases without bound. So again, this limit is an indeterminate form of infinity over infinity, and darn it, L'Hopital's rule applies. I'm sorry, Curtis, I squeezed in an awful lot. I wanted to get this all in one slide. We take the derivative of the numerator. Well, that's one of the easiest ones. It's just e to the x. Derivative of x squared is 2x. And now what happens? Well, as x increases without bound, once again, e to the x is going to infinity, and son of a gun, so is 2x. That's also increasing without bound. And so after applying L'Hopital's rule once, we still have an indeterminate form of infinity over infinity, and we can apply L'Hopital's rule a second time. And let's see, if I did that correctly, once again, we get e to the x in the numerator. And let's see, whoops, I'm sorry, I'm over here, I apologize. And the derivative of 2x is 2, and now I'm good to go. As x goes off to infinity, the numerator is increasing without bound. The denominator is a constant, a positive constant, which drives the whole limit to infinity. And I think someone might ask, well, is it okay to say that that limit does not exist? And in my opinion, yes. This is a special kind of does not exist. And again, I can describe that behavior this way. So this sort of begs the question, we may have talked about this way back in another webinar, but let's take a look at this limit as x goes to infinity of e to the x divided by x raised to the 100th power. So you don't have to do much about that. You could just think a little bit about this one. In light of what we just did, I'd like to know the answer to that limit. And then let's try to draw a general sort of conclusion about this exponential function versus power functions. I think that's important. So any chance, Curtis, somebody can give me an answer to that limit? I don't want them to apply L'Hopital's rule a bazillion times there, but I think they can probably see the patterns here.
I think so, but nobody has responded as of yet. I'll give them just a moment or two.
All right. While they're thinking about that, I'm going to write another one. The limit as x goes to infinity of x to the 100 divided by e to the x. So I'll take an answer to either one of those, actually. What do you get? Curtis, how about you?
Well, it sure seems, I'm just going to go on gut reactions here. I'm not a calculus expert, but it seems to me like if I thought about applying L'Hopital's rule 100 times there, I'm ultimately going to still end up with infinity, going off to infinity in the first.
Absolutely correct. Which is kind of amazing, isn't it? Because if you think about what would be in the denominator, there would be 100 factorial, which is a pretty big number.
Right. That's a really big number.
And therefore, Curtis, what happens with the limit on the right?
I would say it goes to 0.
Absolutely. And two very important limits. And I think the general idea here is that exponential functions grow much faster than power functions.
And see, Steve, I get a little bit of calculus every other Monday night. I get to learn just a little bit more, be reminded of calculus just a little bit more every Monday night. So far I'm doing well.
Very good. All right, I like this example. This is called Don't Forget to
Oh, now you're
Simplify.
starting to get some solutions here. We did have a bit of a delay. So we
Okay.
had Rachel saying infinity. Mark says e to the x wins.
Good. Okay.
And Rachel says 0 for the second. Yeah. So,
Okay. Very good. Well, I think this
and I
is an
did not
important.
have those answers until I said
Well,
mine
you're
already.
saying that now, but all right. Back to example 5 here. I think this is an important idea here. We want to remind students that when they apply L'Hopital's rule, it is important to simplify after applying L'Hopital's rule. Because although I won't do an example of this, if you do not simplify and move on, it is, and say, for example, apply L'Hopital's rule again, it is possible that you will get an incorrect answer. So let's take a look at the limit as x goes off to infinity in this one. Again, as x goes off to infinity, log is increasing without bound. As x goes off to infinity, the square root of x is also increasing without bound. Maybe a little slower, but it's increasing without bound. So this is an indeterminate form of type infinity over infinity. I take the derivative of the numerator, I get 1 divided by x. I take the derivative of the denominator. Well, let's see, that's the power rule, 1/2 x to the minus 1/2. And I rewrote the denominator a little bit here. And if I just kind of look at that quickly, I see that as x goes off to infinity, this is going to 0, and son of a gun, so is the denominator. And so my gut reaction might be to try to apply L'Hopital's rule again. I don't want to do that because it looks like it's going to be ugly just thinking about that. But some students will look at that and say, well, I ought to apply L'Hopital's rule again. Well, not true. What you need to do is to simplify first. And so if I do a little bit of simplification there, a little bit of algebra, this becomes 2 divided by the square root of x, and that's very easy now. As x goes off to infinity, the denominator is increasing without bound, and so that limit is 0. So I think that's a classic example. Make sure that after you, each time you apply L'Hopital's rule, you need to simplify. Here's another one, which I call too much of a good thing. The limit as x goes off to 0 of, wow, e to the x minus e to the minus x minus 2x. Okay, so I won't bore you with all of the details here. This is in an indeterminate form of type 0 over 0. And it turns out that in this case, I had to apply L'Hopital's rule, let's see, I think 3 times in order to get to an answer. And that's fine. Each time along the way, I checked to make sure that the numerator was going to 0, the denominator was going to 0, or again, that we're in an indeterminate form. I applied L'Hopital's rule once again, and I think my final answer down below was 0. So that's kind of a nice example too. I think this kind of a problem where you might have to apply L'Hopital's rule more than once would traditionally appear on the AP Calculus exam in the multiple choice section. I don't know if you'd see one like this in the free response, but I believe we've seen examples like this in the multiple choice. Now, I want to take a little side trip here, Curtis, and just talk about other indeterminate forms. Indeterminate forms of type 0 over 0 and infinity over infinity are really the only 2 types that are tested on the AP Calculus exam, and I'm going to say that with a little asterisk next to it. I'm going to come back to that statement in a minute. But there are other indeterminate forms, and I believe that in most calculus classes taught at the college level, these indeterminate forms are indeed taught and tested. So we have indeterminate products, and this is an indeterminate form of type 0 times infinity. We have an indeterminate difference, infinity minus infinity. We don't know what that is. For example, if this function is increasing faster than g of x is, well, that would drive the whole difference to infinity. Perhaps g of x is increasing faster, that would drive the whole difference to minus infinity. And similarly, there could be some sort of compromise which would drive the whole difference to a constant. There are some indeterminate powers, 0 to the 0, infinity to the 0. This is one of my favorites, 1 to the infinity. That's an indeterminate form. It's not always 1. That limit could turn out to be some other constant. So the basic idea for solving any one of these other indeterminate forms is to simply try to rearrange the terms, rewrite the expression so that we can get it back to something we know about, a classic problem-solving technique. Rewrite it in another form that we know about, 0 over 0 or infinity over infinity. Now, I want to take a quick look, Curtis, if it's okay. This is, Mark Crowley told me about this one. This has actually been talked about on the Facebook page. And in fact, I did it in an AP Calculus workshop last weekend. And some of the teachers on the BC section, BC side, asked me about this. So this is from 2017 BC5, and I'm actually looking at part C. And this problem actually involved an improper integral. And some of the BC teachers out there may remember this one. And I'm just going to take a quick look at the scoring guidelines here if I can. So the way to solve this, or the way to find an antiderivative of this expression, is to use partial fractions. And actually, in the statement of the problem, I'm not going to go back up there, but in the statement of the problem, the students were actually given the partial fraction decomposition. And so there it is. And so what students would sort of naturally do here, I hope, was they would use the partial fraction decomposition and then integrate term by term. Those two antiderivatives are pretty common. They're natural log functions. Minor point, I don't need the absolute value symbols in here because the arguments will be positive on this interval, but that's not the issue. The real issue, and Tom, help me here in case I'm missing something, is if I take a look at that expression and do not simplify it in any way, and do not use properties of logarithms, this expression right here, if I plug in a b, that upper bound, that's going to infinity. That's increasing without bound, and so is this one. And so that looks like infinity minus infinity, which is an indeterminate form, which is not supposed to be tested on the exam. Now, of course, if we rearrange or use properties of logarithms, it's easy to do. Now it's infinity over infinity, and I can handle that one. I know what to do. But this issue came up, and Tom, you have anything to add there?
No, not really. I mean, as you stated, Steve, if you have a form like infinity minus infinity, really the way to handle it is to try to rearrange it into a form that's 0 over 0 or infinity over infinity. And that's exactly what's being done here. So
Yep.
I think that's
okay.
I can see why there was concern by teachers about that.
Yeah.
It looks like it is of that form in the way it's written there. Yeah.
Yep, absolutely. All right, Curtis, I'm going to switch to take a quick look at our problems that we assigned for tonight.
Okay, that sounds really good. Hopefully there's some students out there anxiously awaiting for your solutions here.
Okay. All right, I'm going to try to take a quick look at these. I don't want to take too much of Tom's time. This first and second question, I think, were really cool. So we want to find the limit if it exists. And I know that we post all of these, Curtis, so I won't go through these in too much gory detail. This expression is indeed in an indeterminate form of type 0 over 0. And so pretty straightforward. We take the derivative of the numerator, which is minus the sine of x. We take the derivative of the denominator, which is 1. We can now plug in, use direct substitution in the numerator, and we get, I believe, a -1 here. Pretty straightforward. If we take a look at the limit in part B as x goes to pi over 2 of this expression, of this quotient, again, it's in an indeterminate form of type 0 over 0. We take the derivative of the numerator, we get the cosine of x. The derivative of the denominator, again, is 1. Cosine of pi over 2, 0. This limit is 0. Two pretty straightforward applications of L'Hopital's rule, but I think problem number 2 that ties this together is really cool. So what we ask people to do is to graph these three functions. These three functions are actually the numerator and or the denominator in those two limit problems. And we asked them to graph those three. And so here's what I did. I was using the TI-Nspire, Curtis, on this. Mm-hmm. And I think this is all color coded so you can see the graph. you can understand which graph corresponds to which function here, I think. And right here, I'm going to color a little bit on here if I can. Right in there is pi over 2.
Right.
And so I want to know what's going on near pi over 2. And so I zoomed in near pi over 2, and that's kind of a cool picture. Since these three functions are differentiable, when I zoom in, they should look like they're tangent lines. They should look like straight lines. And in fact, the slope of this one right here, which is the cosine of x, looks like -1. The slope of this one looks like 1. And the slope of this one, sine x minus 1, looks like 0. And so if you just equate all of those slopes and take a look at those limits again, son of a gun, this observation corresponds exactly to the answers we got using L'Hopital's rule. This is a beautiful, in my opinion, visualization of what we just showed analytically.
I like that a lot.
It's really cool. Now, there's one note down at the bottom, and we'll leave this for participants to think a little bit about. But it turns out that these two examples are actually limits of difference quotients. And so you might take a look at the actual definition of the derivative of this function f at pi over 2. That's a classic AP calculus question on a multiple choice portion of the exam. So you might take a quick look at that, and we'll leave that for participants to consider. And Curtis, I apologize. I think this might have been one of the problems here that we may have made a typo on. This should be the limit as x goes to pi over 2 of the secant squared minus the tangent squared of x.
Okay.
And
we'll
I think
make sure to repost that then.
Okay, good. We asked participants to find the value of this limit by writing secant and tangent in terms of sine and cosine. And this is kind of a neat example, because if you do that, which I did right here, I then wrote everything as one fraction. And I believe if you do that, it is an indeterminate form of type 0 over 0. I took the derivative of the numerator and the derivative of the denominator. And that's kind of cool because everything cancels out and I'm left with 1. And this limit turns out to be 1. This is kind of a neat problem. Neat problem. And it turns out, some of you may even remember that this is just a trig identity. So I know that somebody out there is laughing at me, but this one's even an easier one to do just by using that trig identity. We know that secant squared minus tangent squared is equal to 1. Now, one thing you might try to do, and I did not do this in this example, is you might try to graph these two functions separately and then the difference on the same screen and see what happens. That's really a neat idea. And finally here, we had a couple bonus questions too, but I think this was a cool question. This, I think I have a question or two for participants in this one too, Curtis.
Okay.
Let's suppose f has a continuous derivative and the line tangent to the graph of y equal f of x at the point x equal 5 has this equation. So that's the tangent line equation. We want to find this limit. Well, let's see here. Here's the first question. See if I can find it here. I got to take a look at the limit as x goes to 5 of the numerator. And what I did is I took the limit as x goes to 5 of f of x squared as just f of 5. Why is that true? Why can I do that? That's the first question. Why is that limit equal to f of 5? And better yet, why the devil is f of 5 equal to 7? Holy Toledo, where did that come from? Any answers on that one? While you're waiting for an answer, the limit in the denominator is very easy. That's a polynomial. It's a quadratic. It's continuous. The limit is direct substitution, so that limit is 0. Well, what about this one? Why can I go from there to there, and why the heck, how did I know that f of 5 was equal to 7? Any answers on that one, Curtis?
Well, we haven't gotten any answers on that one yet, but Alejandro just pointed out that yes, tangent squared plus 1 is equal to secant squared, talking about that last problem that we were just on. So that gives you an idea just how far the lag is there. But yeah, I'm a little bit interested in as to why you could actually do that.
Well, if f has
I'm having to think a little bit hard.
Well, let's see. If f has a continuous derivative, if it has a derivative, that means it is continuous.
Oh, Mark says the tangent line shares a point at
x equals
that's
5. This reason. Very good. I'm still working on this one. So because f has a derivative, it's continuous, and that means I can evaluate its limit by direct substitution. And then to go from here to here, that's because the tangent line at x equals 5 goes through the point 5 f of 5. And so I'm going to scribble off to the side here. Y of 5, I think, is 15 minus 8 for 7. That's a cool problem. We didn't get to solve it yet. We know it's an indeterminate form of type 0 over 0. A lot of cool things going on here. Take the derivative of the numerator. Well, in the numerator, I've got to use L'Hopital's rule here to take the derivative of the numerator, but I've got to use the chain rule. Derivative of the constant 49 is 0, but 2 times f of x raised to the first power times the derivative of the inner function, which is f prime. And let's see, we know that f of 5 from up above is 7. F prime of 5, where did that come from? How do I know that f prime of 5 is 3? How did I know that? Oh, I know, because the tangent line has slope 3. That's the derivative of the function at 5. So f prime of 5 has got to be 3.
Right.
And a little bit of cancellation, and I get a 21 over 5. That's a cool problem. And finally, I think one thing we asked here was to find the limit by factoring this into the difference of squares. And this is really cool too. So you'll notice here that in the numerator and the denominator, we have the difference of squares. I would suggest that the denominator is a little bit more common way of seeing a difference of squares. And the numerator, yep, it's still a difference of squares, f of x plus 7, f of x minus 7. So, okay, I'm going to do that, and then I'm going to split this up using some limit laws. So that's the limit of this quotient times the limit of this quotient. Well, let's see. This one's pretty easy because it's not in any kind of indeterminate form. I can just plug in an x equals 5. I know that f is continuous. That's easy. We already got f of 5 was 7, so that one's easy. But how do I know that this limit is f prime of 5? Now, you got to think a little bit about that one. It's because this is actually the definition of the derivative of f at 5. I think a little bit earlier, Curtis, I mentioned the alternate definition of the derivative, and that's the alternate definition of the derivative of f at 5. This is a really neat problem. I know that some of you are going to be trying this one with your students tomorrow. That's a really nice AP calculus problem. I could see that on a free response portion of the exam.
I like that.
Sure.
That's a really cool problem.
I think it's a
really cool problem.
Curtis,
just a heads up, Steve, we've got about 15, 20,
yep.
15, 17
I'm going to
minutes,
pass it over
like that,
to Tom. I'm going to leave these bonus questions. We will post these. The bonus questions deal with indeterminate forms, those extra indeterminate forms, and we'll post these on the website. So, Tom, I'm going to pass it over to you, okay?
Okay.
Here we go.
All right. And we'll hope this works.
That looks good.
Great.
Fantastic, Tom.
Okay. Wanted to return to the kind of motivation of L'Hopital's rule. And this is a illustration happened on several years ago when I was first using graphing calculators. And Steve actually went over a justification for L'Hopital's rule But I wanted to look at that again a little bit more geometrically. So what I've got here are a couple of lines. One is in red and one's in green. And notice that they have the same x-intercept right here. Now, these two lines, there's the scaling here, there's nothing funny about it. 1 unit in the x direction, the same as 1 unit in the y direction. So I'm not playing any tricks on you in terms of scaling. But what I'm interested in is the ratio of the y values of the red line to the y value on the green line for the same x value. And so, for example, here, looks like the red value is 1 unit up, and the green value is 1/2 unit down below the x-axis. So that ratio would be 1 to -1/2. Over here, it's like a ratio of 2 units to -1. Guess that ratio would be the same. Over here, we've got a ratio of -3 to +1.5. So in each case, we're getting a ratio of, I guess, what would it be? -2 for the red over the green. And now what I want to do is look at the ratio of the slopes of these two lines. And here, the red line, well, it looks just like a diagonal line. So that's got a slope of +1. And the green line has a slope of -1/2. We're going down 1 unit for a run of 2. So the ratio of the slopes is 1 over -1/2. That's also -2. So the ratio of the slopes of these two lines is the same as the ratio of the y values for any x value. Makes sense. And that's not true for any two lines. Or the reason this works is that these two lines share an x-intercept. Okay, so the ratio of the slopes is the same as the ratio of the y values.
That's cool.
Well, I did lie a little bit. It turns out that this was a zoomed in picture. Those weren't two lines. They were the graphs of two differentiable functions that had a common 0. So if we think of this as this x-intercept as the value a that Steve was talking about, notice you've got your f of a and g of a are both 0. And we could see with lines, the ratio, if you have a common x-intercept, the ratio of the slopes will be the ratio of the y values, except at that one point, of course, where 0 over 0 is indeterminate. But this is really a geometric way of seeing why L'Hopital's rule works, which is, I think, kind of cool. So that's the motivation there. I'm going to switch technology use here. I'm going to switch over to the TI-84 to look at some other things. I'm going to take Steve's invitation here. I had several functions loaded in. Some of these you might remember he graphed these on the TI-Nspire. The function that he looked at earlier was the natural log of x divided by x minus 1. And he was curious about just looking at the graph of that and seeing what we would get. Okay, let's do it on the 84. I'm going to, let me just use a zoom decimal window. I like to zoom decimal windows because it's basically each pixel is 0.1 in both directions. So it preserves slope with those equal units in both x and y. And so let's go ahead and look at that graph. And I've always thought this was so cool. We made ourselves lucky here. The interesting value, Steve was looking at the limit as x approaches 1. And notice you can actually see a hole in the graph. So this is the graph of the quotient, natural log of x over x minus 1. And this is what we call removable discontinuity. The graph actually looks nice and continuous, except at that one point where we have a hole. And if we were going to fill in that hole, we would guess the value 1. And that was the limit that Steve ended up with by using L'Hopital's rule. So again, that's very neat. Let me go back to the y equals menu. I just want to make a point that, again, about this power of local linearity. I'm going to look at just the regular sine function here. And so let's take a look at that graph. Okay, that's an old familiar sine function. And what I'm going to do here is I'm interested in exploring the derivative of this function at x equals 0. And I'm going to do that simply by zooming in on the graph. So let's zoom in. And I'm right there at the origin. That's where I want to be. Okay, let's go ahead and hit enter. And once I've activated zoom in, I can just hit enter again and continue to zoom in over and over again. And it doesn't take very many zooms before, remember, we're looking at the graph of the y equals sine x, but it looks, for all intents and purposes, like y equal x. That's really pretty profound. I mean, what that says is sine x really behaves a lot like y equal x when you're near x equals 0. And I think Steve had a limit earlier. He mentioned the limit as x approaches 0 of sine x over x is 1. That's because those two functions are behaving so similarly. So that's this power of local linearity. That tail of two lines illustration from earlier, we were looking at the zoomed in part first and zoomed out to reveal that they were actually two differentiable functions. But here we're zooming in on the graph. And for me, I think this is it's actually a really robust way to think about what it means for a function to be differentiable. It means that up close, it behaves a lot like a linear function. And that's a really nice property to have. Well, with time permitting, let's maybe go back to y equals here. And these are those three functions that Steve was looking at earlier. Let me go ahead and hit activate each one of those. These were
hey Tom,
yeah.
I think, I don't know, maybe it's just Curtis and I, but we're having trouble seeing your TI-84 screen. For me, I see your TI-Nspire screen. I don't see the 84. Is the 84 up on yours?
Oh my gosh, I am so sorry. So I think what I need to do is select another. So I'll tell you what, let me do stop share. And then I'm going to share screen again. And this time pick the 84. That
there it is. There it is. I think all of us missed that. I was fearing. Yeah, I was having some issues, so I wasn't sure.
On my machine, but with the Zoom, we needed to do this. So, well, let me.
Can you do that just a moment again, just really quick?
Absolutely.
Sorry, everyone out there. I didn't catch that. I wasn't seeing it, but I also had some issues with internet. So.
Okay. So one of the things, so let's try this again. This is that function that Steve had mentioned before, natural log of x over x minus 1. I thought I'd just look at a zoom decimal window of that. And I've always found this as neat, is that as long as the point lines up exactly with a pixel, you can actually see the whole in the graph.
And that's super powerful. I really like that. That is a really key thing. And I know, Tom, you and I have talked about that in the past as one of those places where you saw the super advantage of using technology to teach this.
Yeah, it was literally the first day I ever used graphing calculators was in a calculus class. And I was graphing function limit, and I was having the students say this first time any of them had used a graphing calculator. And I remember the hair standing up on the back of my neck when I was hearing those. students saying to each other, hey, my graph's got a hole in it. Does your graph have a hole in it? What's going on? And I knew, wow, there's the hook. There's something weird has happened and they want to understand what it is.
Yeah, that's awesome.
And we can even trace on this as we get close to x equal 1. Oh,
yep.
And fine. There it is. Y equals blank. But if we were going to fill in that hole, we'd fill it in with y equals 1 would remove the discontinuity.
Right.
And that was the limit that Steve found using L'Hopital's rule.
Yeah, that's perfect.
So Tom, maybe I can set him up and you can knock him down. Let me ask you one other question about this. Okay. So let's just suppose that the limit as x goes to a, where a is not a nice number. It's not a 1.1. It's not an integer. But there is a hole in the function, in the graph of the function, and I'd like to see that hole. Is there any way that I can graph that? Is there any trick that I can use to graph that so that I will guarantee that the hole is present? I know what I do. You're much better at this than I am, but I know what I would do. I would graph it so that that value A is smack dab in the middle of x min to x max.
Yeah, I think though the problem is if that value A happens to be irrational,
it won't work.
To be out of luck because no matter what, I mean, our pixel coordinates are all going to be rational
numbers,
very ugly and out to 10 or 11 decimal places. They're still rational.
So if it was
I'll tell you what we could try, Steve, is on y. The first problem from the problem set.
Oh, yeah, there you go.
Had these 3 functions, and that was a value of A.
Yes, sir.
That was not nice in the decimal sense, right? It was
yes,
pi over
right.
2. Pi over 2 is a nice number trig-wise.
Yep.
So what I'm going to do is I'm going to try graphing this in a trig window.
Okay.
The trig window is set up so the hash marks on your axes on the x-axis correspond to nice multiples of pi.
Okay.
So I'm going to go down to zoom trig. The thing is, even zoom trig, I'm going to doubt that we're going to see. Oh, of course, all these functions are defined. We'd have to actually do one of the quotients, wouldn't we?
Yes. Yeah.
So let's try that. Let me go back to y equals, and I'll just.
Well, just go down to y4 and put in.
Yeah, y3 over y1.
Yeah.
Or y2 over y1. Why don't I do that?
There you go. y2 over y1.
All right. There's y2 divided by y1. And let's graph that. Again, we're in, I think, this is a, well, let's see. I thought we were in a zoom trig window. Let me see. There we go. So even though we're at nice multiples of pi here, because it's decimal, I'm not seeing that hole.
Yeah, interesting.
Yep.
So just for the heck of it, try a window where pi over 2 is the center. So graph it from like 0 to pi.
Okay.
Can you do that?
Sure. 0. Let's see. Here's pi right over here. Now notice though what happened there, Steve.
Yeah, yeah, I understand.
As close as it could get.
Yep.
So let's go ahead and graph and see
what happens. Yeah, you don't get it.
So there it is. Pi over 2 is right in the middle of my window, but it's not right on that value because of the decimal approximation.
Well, there's a good challenge then, huh, Tom?
Yeah, that would be. I'll have to think about that. I'm not sure.
Okay. Or maybe some of our participants would think about that, Curtis, too.
Yeah, I think so. And I think this is a great example of some of the, some of the things that we think about with numeric devices and, when you're dealing with approximations of pi or approximations of irrational numbers. That's always a something to think about as you're making these these learning tools.
Yeah.
Well, Tom, that was
apologies for fumbling with the technology earlier when I changed over to the 84. I think
that's okay. I should have called out a little earlier. I was having some internet issues, so I wasn't sure if it was just me or not. Well, Tom, it looks like we're right at the end of our time slot for this evening. And so I want to be conscientious of your time and of our participant time and everything that way. But I sure enjoyed it, Tom and Steve. Really enjoyed having you guys with us again this evening. And I just want to put another reminder out there for our participants. And that is that we will be posting the solutions to this week's problems and the upcoming series of problems coming up for our next Monday Night Calculus 2 weeks from now. What is that? October the 26th. We'll have another one of these sessions. Really look forward to working with Tom and Steve again in a couple of weeks. And I certainly encourage any teachers out there who haven't gotten their students involved and having them on here to ask Steve and Tom questions. This is a great opportunity to interrupt Steve and ask him a question related or not to what we're talking about in that particular session. It's always good. We want to have some participation. And so that's always a nice thing. So anyway, I just wanted to again, thank you, Steve and Tom, for all your hard work. And we'll see you guys in a couple of weeks. How's that sound?
Thank you, Curtis. That'll be a Halloween edition.
All right. Good. That's right. The Halloween edition. Good night, guys.
Good night.